Hi everyone. Today I will walk you through my exploit demo assignment for the course Ethical Hacking. So the exploit that I chose is a vulnerability that exists on Solidity smart contracts. So Solidity is a programming languages in which one can write smart contracts, and this language is particularly used on the Ethereum blockchain. So on smart contracts, we have a few registries or categorizations that describe vulnerabilities that can exist, though these ones usually are connected to the version of Solidity that's been used. In this case, we call it Pragma. And one that was for many years on the top most dangerous vulnerabilities was reentrancy. And a definition of reentrancy is that a smart contract has a vulnerability when it allows to external contracts to access or re-enter a function and repeat actions uh, on their demand. So because of this, someone can take over a function and call it several times. So sometimes this function can be doing something really benign, or maybe just changing a variable that won't end up in losing money, but it can also be connected to money transfer, and then you have a huge leak of Ether, which is the currency that it's used in the Ethereum blockchain. So there are five different types of vulnerability. The one I will focus on is in the first one is the single function reentrancy, when it's called directly in a function instead of, for example, cross contract, which is one contract can connect to another one, exploring the exploiting the smart contract, and in these cases either could be drain sources or changing states of variables, but I will focus on the first one. So the example here is that it usually happens with a function that allows you to take money, like withdraw. So you have a reentrance contract that has the functions donate, withdraw, and then you have the reentrance attack contract. So what it will happen is that they will deposit money on the contract that has the vulnerability. So this will look like a benign action. And then when they try to withdraw the money, they exploit the vulnerability. So when they have this call, which is message.sender.call.value, they obtain, or not necessarily obtain, but they use the vulnerability to use the function, the fallback function that before it was written with these parentheses, but now in newer versions of Solidity is written fallback. But what it means is that the function that runs when something doesn't go through. So they use the fallback function to repeatedly call the withdraw function until they are out of gas or out of money. So gas is what you use on blockchain to pay for the execution of a transaction. So they will repeatedly call until they are out of gas, or when the money they pay for executing their call ends, or when the vulnerable contract runs out of money. So I did the exploit on a Docker image, and what it has is a hard hat project. So hard hat is a testing framework for Solidity, and you can find it on the Docker image I created, but I have it also here for you to see. So let me just move this. Oops, there we go. So this is the hard hat project, is the thing you will get when you use the Docker image I added. So what's important here to know is a JavaScript project, and you had some configurations. In this case, I added two compiler versions of Solidity, so 0.4.24 and 0.4.25. As I mentioned on my assignment, the Solidity version that still is vulnerable to this kind of attack is quite old, so it's 0.4. Today we are in 0.8, but up to date we can still find contracts that have this version. And since there's no many people who are very knowledgeable about smart contract development, it's common to still find this error, and therefore it's still valuable to study and show an exploit like this. So in the hard hat framework, you will have the contracts that you want to test, and then there is a test orchestrator that is the one that represents the blockchain. Because if I were to recreate the exploits on the Ethereum blockchain, I will have to spend quite some significant money. But we can use this testing framework to show how the exploit will be. So here we have the original contract, which actually is a real address. You can find it on Etherscan and see that the code is exact same. So this contract has its name personal bank, and it has a mapping when they save balances. For this is usually so some contracts sometimes want to execute a few functions. This one is actually a bank, but it's normal to find this mapping address when they store the balances of their users, so they can operate with different functions. In this case, they allow you to deposit money on your account, and you can collect what you had in your own account. So in smart contracts, message.sender comes from the person who is calling the function, and that's why they use it to store the value. And as you can see, this is the fallback function, which has a deposit. So it means that this will be called when here. So every time this line of code executes, if it doesn't work, it will go back to deposit. So it will, if this sending doesn't go through, it will deposit back the money. And they have another contract, which is a log, that helps to as a normal log in any other programming language. So I created this attack contract that what it does is has a function deposit that allows you to call the deposit function on the vulnerable contract. So this is a benign function, but then the attack, what it does is it receives the money you want to start the attack. It must be at least 1 ether, because on the original contract, they said that if you want to yes, so they said that in order to collect, you have to have a minimum amount of money, and the minimum amount of money is designed as 1 ether. So that's why I put that it has to be bigger than 1. And then you call collect, and how does the reentrancy attack goes is that the variable function here will check that we already started the attack, and then as long as the balance on the vulnerable contract is bigger than 1, it will keep calling collect. So it will iteratively collect until the contract runs out of money. So now you will ask, but how does it get the money? So as you can see here, in order to collect the money, there are some checks in the vulnerable contract. So they ask you that you have at least 1 ether when you're trying to withdraw the money. And they ask you that you have more money than what you want to collect, right? And then they ask you to they go at if message.sender.call.value. So then they are sending that money back to you. So then you are withdrawing the money. And this if means that it doesn't go through. But as I mentioned before, when this function doesn't go well, then if we are the ones who send it, if we are the attacker, and if it doesn't go correctly, it will call this function, which is the fallback function. And with that, we take ownership of the contract, or we force us to stay in that endlessly iteration until we collect all the money. And why does this happen? Because when they are sending the money, they update the value of your balance after they have sent the money. So we can take as much as we want until it runs out, because they are not updating our balance. So according to them, they can still send the money. And this is written on the hard hat test in the following way. So we get the contracts that we have in the contracts folder, and we deploy them. And then we have the test here, so that it should successfully drain the funds through a reentrancy attack. So we add money on the victim because we are recreating the blockchain states. And then we check that the victim indeed has 5 ether. So then we have the benign action when the hacker deposits 2 ether. So it's a normal user, it's just adding money. And then we check that the victim before had 5 ether. It did have the 5 ether, and now the hacker deposits 2. So now we expect the victim to have 7 ether, which is still okay. And then just to make sure that the attack went through, we set the hacker's balance to 0. So then we execute the attack with 2 ether, and we obtain the balance of the bank, the vulnerable contract, and the hacker. So as you saw before the attack, the hacker had 0 money. So if the victim had 7 ether. So if this were to be a normal interaction, the personal bank balance should have 5 ether. If you have less than that, then it means that we took more money than what we should. And the hacker balance, as it intended to withdraw 2 ether, if it was benign, the balance should be 2 ether, but if it's more than that, it means that we earn money. And how do we run this? So here in the console, I'm not sure if you can see the zoom bar, but let me move it. Oh no, okay. So we have npx, hard hat, and then we can just say test, and this will run all the tests that are in the project, but in this case, we only have one. And we can see that the test passed, so this assertion, which in hard hat is expect, all the expect pass, and it means that the hacker got the money. So what we did is that, as a summary, we use hard hat as a tensing framework to recreate the behavior on the blockchain. This is how we can show that an exploit exists, but from a hacker perspective, this lets you test your possible attacks before you actually execute it on the blockchain, because if sometimes these vulnerabilities might not be the owner of the vulnerable contract might not be aware. So if one has a unsuccessful attack, maybe it will raise the alarm and they will discover the vulnerability. And even though upgrading contracts is not fast or easy, what they can do is they can take the money from the contract to a safer one. So as a hacker, you really want to test that your attack will went through, if you can, of course, before actually executing it. So what I added on the test file, on the exploit file, is how you can run the exploit using Docker. And what we saw on the video is when we get this pass on the test, it means that we actually managed to get the money from the contract. So I add the disclaimer that I mentioned before, that the reentrancy vulnerability is considered obsolete or almost obsolete on the latest versions of Solidity, yet one can still find it in projects up to date. So it's still relevant to study. Thank you so much.